So our lesson for today is going to be talking about triangle similarity specifically. We talked about similarity in general last time. This is going to be talking about the 3 rules to prove whether triangles are similar or not. Hopefully this kind of looks familiar compared to Unit 4. You guys remember we talked about congruency. We had 5 rules. We had side, 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 angle, 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 side, and HL. Okay, we had 5. For similarity, we just have 3. Okay? We have angle, angle similarity, side, side, side similarity, and side, angle, side similarity. Notice how I have a little squiggle here. The reason why that's there is particularly for these two, so you guys can distinguish them from the congruency rule versus the similarity one. So when we're talking about similarity, please make sure you include that little symbol there so you're able to distinguish the difference between those. Today is where we're going to be talking about proofs as well. The proofs that we're going to have for similarity are almost exactly the same as they would be for congruency. We're just switching the concept here to prove that they're similar instead of congruent, but the general structure is going to be the same. Alright, so the first rule of the 3 that we're going to talk about is angle, angle. So hopefully you guys remember when we talked about congruency, we were talking about the 2 rules that didn't work for congruency, right? For congruency, angle, angle, angle doesn't work, and side, side, angle doesn't work, right? For congruency, you can't prove that triangles are congruent with just angles, but you can for similarity. And since these rules are based on the least amount of information that you need, they just choose 2 angles. You could have all 3, so technically angle, angle, angle would work, but since we only need at least 2, that's why there's only 2 A's instead of all 3. So this rule says 2 triangles are similar if they have 2 pairs of corresponding congruent angles. They could have all 3, right, but they need at least 2. Just 1 pair is not going to be enough. If you have at least 2 pairs of congruent angles, that is enough. So this is an illustration. If you guys see that you have 2 pairs of congruent angles, you can say that the triangles are similar. And so we're going to practice with similarity statements. It's the same thing as congruency. Please make sure you name the shape in the correct order. So if I name this one HOT, I go from the double to the single to the one that's unmarked. How would I do the same thing over here? C and then L. Okay, so please make sure that you understand the ordering of the letters is still relevant here. All right, the next one is called side, side, side similarity. This rule says 2 triangles are similar if all corresponding sides are proportional. Side, side, side for congruent triangles said that the sides had to be congruent, but we're switching the concept to similarity this time. So instead of them all being the same, they should just be proportional. We actually tried this last time where we checked to see that the angles were congruent and the sides are proportional. This is a rule that's only asking for the least amount of information necessary. So for this one, you don't need to know anything about the angles. You just need to check to see if the sides are proportional. Now notice how it says corresponding, so you do need to make sure you're matching up the correct sides. And because they don't give you the names of the shapes, you can't tell what sides are corresponding by the name. So instead, there's a really easy system you're going to use. You're just going to match the shortest sides together, the medium length sides together, and then the longest sides together. So for instance, in this triangle, what would be the shortest side? What's its measure? 3. You're right, AB, and its measure is 3. So I'm going to compare that measurement to the shortest measurement over here, which is 4. Okay? And then I'm going to compare the medium length over here, which is 4, to the medium length on the other one. And then the longest 2. So you want to check these measures. What you want to do is put each of these in the calculator and see if each one of these ratios ends up being the same thing. If that happens, if this is equal to this is equal to this, like that's represented right here, then the sides are all proportional and the shapes will be similar. Okay? So in this situation, you don't need to know anything about the angles. You just need to know that all 3 sides are proportional if you match them up in the corresponding order. So if I know that these 2 are similar, how would I name the second triangle? If I go A, C, B, what corresponds to A? P. What corresponds to C? Q, and then what corresponds to B? Right? And the way you can figure that out, if you need to use the sides, you can say the angle between the medium and the long. You can do that over here, medium, long. You can see how they match up that way, if they don't have any markings. Right? Then our last one is side, angle, side. Again, very similar to the congruency one, but instead of the sides being congruent, they're going to be proportional. So the angle needs to be congruent. So you have 1 pair of congruent angles, and then the 2 sides that are surrounding those angles need to be proportional. However, for similarity, the angles are still congruent, but it's the sides that switch to something different, specifically being proportional. So in this scenario, right, remember in Unit 4, sometimes our triangles or our shapes didn't have all the information up front, so sometimes you may need to add information. Is there anything I can add? I can add vertical angles. There's the A from your side angle side, right? You need one pair of congruent angles. Then you're going to check to see if the sides surrounding those angles, we're going to see if those are proportional. Right, remember the sandwich still applies here. The angle needs to be between the two sides. So I'm going to compare short to short and long to long, just like we did in the previous one. So in this triangle, the shorter side is 2, and in this triangle, the shorter one's 3. The longer side in the other triangle is 2.5, and then you compare that to the 3.75. You want to put that in your calculator. You want to check to see if it's proportional, which means that those two fractions or ratios would give you the same decimal result. So what do you guys think? Yeah, you should get the same number. So if you have that happening, if you have the one set of angles being congruent, and then the surrounding sides, as long as you match them up in the corresponding order, if those are proportional, then the triangles are similar. How would I name, if I have this one, EST? AST, yep. Alright, so everybody clear on how to use those three rules? We're going to do a bunch of examples. Looking at these, we're going to determine if the triangles are similar or not, and explain why for whether the answer is yes or no. Right? So for this one, hopefully you guys should notice that there are no sides. You see how there are no side lengths? So it's the only rule that I could attempt to use. I can only check to see if angle works. Right? Which means I need at least two pairs of congruent angles. Right now I have one. Just glancing at this, seeing that I only have one, do I just rule this out, say no, and move on? Is there more I could do here? What can I do? I can figure out the other angles, right? So if I do the triangle sum theorem, the 40 and the 72 added together, if I subtract that from 180, what do I get for the missing angle? 68. There's your second angle. If you were to keep going, you'd get that these two are congruent as well. But remember, you only need at least 2. So you can stop once you have the 2. So would these triangles be similar? Yes. Using angle, similar. Alright. Over here, I do notice I have side lengths now. But which of the two rules that uses side lengths can I not use? Which one of the three rules can I not use that involve sides? Why? Why can't I use that? It's not based on the sides that I already have. Because I don't have the third side, right? I can't check if all the sides are proportional if I don't know 2 of them, right? So what do you think the rule would be that I test for this scenario? I'm going to test side, angle, side. Hopefully you guys notice that I have 2 parallel lines here. What do I get from parallel lines? I get these alternate interior angles using the Z trick that we've seen before, right? So that's the A. I have the one set of congruent angles. Do I have 2 pairs of congruent angles? Can I get a second from those parallel lines? No. So I can't use angle either. Side is ruled out because I don't have enough information. Angle is ruled out because I can't get the second set of congruent angles. So now what I have to do is check to see if the sides are proportional, right? So we're going to go back and forth between the 2 triangles. In the upper triangle, which side is shorter? Okay. In the bottom triangle, which side is shorter? Bottom triangle. The 18. In the upper triangle, which side is longer? 18. And in the bottom triangle, which side is longer? The 24. I'll explain why we have to use 18 twice in a second, but you compare short to short, long to long, then you put that in your calculator and see if those ratios are the same. Are these two the same? Yes. So if I know that I have one set of congruent angles and then the pairs of sides are proportional, would these be similar? Yes. That's all you need to prove that side, angle, side similarity works. Right? Now, there's a slight discrepancy here compared to what we've done in the past with congruent triangles. You guys remember the reflexive property? Where we would say that overlapping side is equal to itself. That still is true. It's still true that RM is 18 and MR is 18. It's equal to itself. But the reason why we don't use reflexive the same way in this scenario is because this triangle has been shrunken and then kind of reflected and twisted, right? So this 18 is serving two different purposes. The 18 is serving as the longer side for this triangle, but the shorter side for this triangle. So that's something you guys need to be careful with. These sides, when they're overlapping, will be serving different purposes in each triangle. So don't try to use the reflexive property in proofs in the same kind of way that we were doing with congruency, because we're not trying to say the sides are congruent, we're trying to say that they're proportional. And they mean different things for each triangle. So we're not going to be using reflexive in the same way before. No. Okay, everybody good with the first two? So all you need for a side angle side is to get the angles to be congruent, right? And then make sure that the corresponding sides are in the same ratio. So if you plug these into the calculator and get the same decimal, then you're good. All right, what about this one? This one would be no, they're not similar, and the reason why is because we don't have enough information. Right? Based on what we know, we can't say that they're similar, so we say no. They technically could be if we had more information, but we don't have that. So the only conclusion we can make is that they're not similar. Because we don't have two sets of congruent angles, we have one set of congruent angles. But remember, it's angle, angle, not just angle. So because we don't have enough information, you just say no. Alright, what rule would I try for this one? Side, side, side. Because I don't know any angles, this is really the only rule I can test. Alright, so let's take a look. What's the shortest side in this triangle? What's the shortest side in this triangle? Alright, so we're going to compare those. What's the medium in this triangle? 15 compared to 20. And then the longest side, 18 compared to 24. Just like we were doing before when we were writing proportions, please make sure you're going in the same direction each time when you're writing the ratios. And when you plug these into your calculator, do you get the same decimal result for all three? No. These two should be the same. Okay. This is the one that's not the same. If at least one of those relationships is not the same as the others, then you would have to say that they are not similar. Now, the reason why we're going to defend our answer is not the same as up here. Up here, we said they're not similar because we didn't have enough information. Over here, what you're going to say is this. So there are two different ways that you guys could say no. It's when you don't have enough information, and then the second way is if you try a rule and it doesn't work out. So if you have plenty of information, we have the exact amount of information we need to check for side, 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 but it didn't work. So the reason why they're not similar is because the side, side, side rule failed. Okay, so please make sure you're defending your answer, whether it's yes, no, not enough information, or no because one of the rule fails. Okay? All right, what about this one? I can use supplementary to fill in that. So now I have one pair of congruent angles. Do I have a second pair of congruent angles? No. So what's the rule I'm going to try? Side angle side. I have the two sides that are surrounding the two angles that are congruent. So that's the rule I'm going to be checking here. So in this left-hand triangle, what's the shorter side?
No.
5. 4 is not a side, it's part of a side. So the shorter side is 5 in that triangle. What's the shorter side in the other triangle? 3. And then what's the longer side in the left-hand triangle? 10. That's where the 4 comes into the picture. You need the 4 to get the full length by adding the 4 to the 6. And then what's the longer side in the smaller one? Alright, you shouldn't use your calculator. Are those the same? Yes. So if you have angles, one pair of angles are congruent, the surrounding sides are proportional, then the triangles would be similar by side angle side similar. Okay. What about this one? What rule do you think I would use for this? This was a little bit of a trick question. Angle, angle, why? But they give me sides, why wouldn't I use side, angle, side? Or did they give me sides?
I saw some of the sides are congruent and the angles are congruent too. So
Okay.
So it'd be another 71 on that side. And then you could figure out what the other angle was by adding those up and subtracting by 180.
Okay.
And then the other side, you just subtract from 180 and then
Okay, so what are all those results then? What do I get as the vertex angle for this one? What do I get as the base angles for that one? And then this one, right? So the easy thing, and I'm glad you guys didn't fall into the trap that easily. One of the easier things to fall into as a kind of trap when they give you these kinds of questions is when you see these markings, you try to use side angle side because we see that the markings are provided. But can you check proportionality if you just have a marking? Is that a number? You can't check proportionality if you don't have actual numbers. So even though they have markings on the sides, this is not side angle side. Because you need to check that the angles are congruent and the sides are proportional. You can't do that with little hash marks. Okay? The only reason why these hash marks are here are, like you guys said, is because they're isosceles, so you can use those to figure out the angles. The angles are what we're focusing on here. Right? So can I say that these triangles are similar? Yes, I can. Which rule? Angle, similarity. Right? I do have all three of them being congruent, but you just need at least two for the rule. Alright, I'm going to let you guys try the bottom row by yourself. So go ahead and work through those three, and then we'll move on to the next page. Alright, hopefully when you guys are working through this question, you should have noticed that we had two sides provided, so I can't use side, side, side. And I don't have enough information in this triangle to find more of the angles, so I also can't use angle, angle. The only rule I can attempt to use is side, angle, side. When you guys use triangle sum theorem, you should get 80 here. So that's the A part. And then when you check to see if the sides are proportional, they should be the same. So these should be similar by side, angle, side similarity. Yes? Okay. And this one, all we know is that we have two parallel lines. There's nothing else really given to us here. So what can I get from them? How? Okay. You could do the Z trick twice if you wanted to. Right? You could use either of the two transversals. When you use the vertical and then the parallel lines to get another set of alternate interior angles being congruent, that's enough information to say that they're similar by angle similarity. Okay? And then for this one, they are overlapping, but hopefully you guys can see the two separate triangles. For this one, what rule would I want to use? I have side, angle, side for each of them. I just need to check to see if the sides are proportional. I already have that the two right angles are congruent. So when you test the sides, so let's say we're going short to short. So the 8 is the shorter of the one on the left compared to the 10 on the right. And then the long side on this triangle is 14 compared to 12 on this one. Are those two ratios the same? No. So these would not be similar, and how would you defend your answer? Side, angle, side. Okay. That I'm not too worried about. It's the ones where you say yes, I want to make sure you can distinguish between congruent and similar. Alright, we have a bunch more here that we'll just quickly go through. Everybody's pretty comfortable with this so far, right? Okay, so I'll go through these pretty quickly. So what kind of triangles would I call these? They're both equilateral. What do I know about the angles of equilateral triangles? Are equal, right? So I can do boom, boom, boom. Now, since these are single marks, right? Over here, these are double marks. Does that mean that I have to use double marks to say that these angles are congruent? Can I also use single marks here? Do you guys remember what the specific measure is? 60. So 60 is the same for every equilateral triangle, regardless of whether you have single marks or double marks or triple marks, whatever. No matter how big or small the equilateral triangle is, all the angles are 60. So all these angles are congruent to each other. So would I say that these are similar? Yes. All equilateral triangles are similar to each other, by definition. Right? For this one's kind of been helter-skelter. We have one smaller triangle inside of a bigger one. It's the only thing that happened is that the big triangle was reflected and then dilated to get this relationship. So I need to find the missing angles. Obviously, I don't have any information about the size, so I can only rely on angle, angle here. So if I find this angle, what would I get for that one? If I find this angle, what do I get for that one? Okay, so what can I conclude about these triangles, the big one and the small one? Can I say that they're similar? No? Why? We have plenty of information here. triangle fails. There are no pairs of congruent angles. Even if there was one, it would still fail because you need two sets of congruent angles, and we don't have any. Okay? Yes?
How did you get this number?
So see how there's a bigger triangle right here? I use the triangle sum theorem, ignoring these two. So I had 80 and the 25, tell me find 75. Alright, what about over here? Obviously no side length, so I'm going to be testing angle, angle. I have one set of congruent angles, so that's one. Can I find another? And how? Yes? Alright, so I have parallel lines, and then what's the transversal that would be most helpful? Okay, you see the horizontal one right here. So what congruent angles can I get? Those two right there, corresponding. You don't always use the z-trick. It is most common that you use the z-trick to find angles, but you could still use corresponding. So please make sure you're not ruling that option out. And it typically happens when the two shapes are touching, they're right next to each other like that. That's typically when the corresponding angles come out. Alright, so I have two pairs of congruent angles, so would these be similar? Yes, by Alright, now these ones are examples with overlapping triangles, where we have triangles kind of embedded in a more complicated diagram. So that's why I've given, and this is a typo, the symbol for congruency is way easier to accidentally use than the similarity one. I'm trying to see if those specific triangles are similar. So we're going to take a look. When they give you the names, that's usually really helpful to use to figure out what sides are corresponding. So I'm trying to see if NBS is similar to NMC. So you guys see how they kind of switch the directions and how they name them? We have to be careful when we're writing the proportion with that pattern. So let's say I'm checking, well hold on, which rule would I use? Side, angle side. Where's the angle? N. You guys see how both names have N in common? That's a reflexive. The reflexive angle property you can definitely use. It's the reflexive side property you want to stay away from. But here they both have N in common. So that's the congruent angle that you're looking for. Now we need to check to see if the sides are proportional. So I have the smaller triangle. If you want to, you can draw them separate. Like that. Draw them all separately from each other. That's 16, that's, I drew over it. Is that a 9 and a 3? Alright, so we can go like this. Now, since they've given us the names of the triangles, we're going to use the name to figure out what's corresponding, even though you can still use that short to short, long to long pattern. So I want NB, which is the 6, compared to NM, which over here is the 12. So you can either draw them separate or just go off of the picture. The NB and the NM correspond. And then the side, which one have I done? NS, this one right here, the 9. NS compares to NC, which is this side, the 6. I added that wrong. I don't know, I did that. 18. Sorry. 18, not 16. Alright, so when you piece the sides together using the name or with your redrawn diagram here, are those two ratios the same? 6 over 12, 9 over 18. Yes, sir. They both simplify to half, right? So would I be able to conclude that these two triangles specifically mentioned, would those be similar? What rule would I use? Side angle, side similarity. Alright. This one is specifically referring to DSY and RSA, which is right here. What rule would I try? I'm going to try side angle side. You should notice that you have two sides per triangle, and then is there a way you can get that congruent angle? Vertical angles. So if you use vertical angles, that gives you the A part. Now I want to check to see if these sides are going to work out with the proportion. Again, you can use the name system to see what corresponds, or you can compare short to short, long to long. It should work out either way. So in this triangle, the shorter side is 10. What's the shorter side over here? 6. And in this triangle, the longer one is 18. Over here, the longer side is 30. Are those two ratios the same? No. This one's greater than the 1, this one's less than 1. So clearly they can't be the same. So would those two triangles be similar? No. So we say no, And then what's the reason? Okay. And then lastly, what rule would I try for this one? I'm going to try side, side, side. We're comparing NCB, this one right here, to NAC, the one right next to it. Okay? So, short to short, medium to medium, long to long. We're going to compare 9 in this triangle to what side of that triangle? 12. I'm going to compare 12 in the left-hand triangle to what side in the right-hand triangle? 16. And then 15 to 20. Double check to see if those are the same. Yes, they are. So these would be similar by side, side, side. Great. So all sorts of different scenarios you guys could run into. Just make sure you understand how to use those 3 rules. Alright, we're going to move on to a little bit more practice with solving. This right here, this box is a review of the types of questions we've seen already. So I just want to review that. And then the rest of these are different, the way that they're set up. We're going to be talking primarily about diagrams I call nested diagrams. Do you guys know what nested Russian dolls are? You have, they're kind of split in half, and you pull off the top, and inside of the bigger one is the smaller one. Open up the top, there's another one, and keep going down like that. The basic idea of that is that you have a doll inside of a doll. It's like Inception. So I call these nested diagrams because you can see that there is one smaller triangle inside of a bigger one. So the way that we work with these is going to be a little bit different, specifically looking at the labels and knowing how to work with them. So I'm going to train you guys how to do that with these different scenarios. Excuse me. But first we're going to review what we talked about last time. So let's say I wanted to solve for x first. How would I set up the proportion? Oh, by the way. Anytime you see similar, we're going to be using proportions to solve. How would I set up the proportion for x? You're going to start with the variable expression. It's a good consistent pattern to use when you're creating proportions. So start with the variable expression, then write that over top of what it's corresponding to. 12. And then you're going to write the scale factor, or the 2 sides that help you create the scale factor, whether you want to simplify or not, doesn't matter. 5 over 4. Good. Please make sure you go back to the original triangle when you write that ratio. So this is your proportion. You cross multiply. 12x minus 4 is 60. 12x equals 64. X equals 5.3 repeated. Everybody with me for x? Alright, how would I do the same thing but for y? 4y, start with the variable 4y over 20. So these 2 sides are corresponding. And then what scale factor would I use? What's the second ratio? 5 over 4 again?
4.
No, this time you'd use 4 over 5. You see how y was in this triangle? You see how we switched triangles to start? So you have to make sure in the second ratio you go back to the original triangle where the 4y came from. That's the 4 this time. So please make sure you remember what shape you started in. So this is now the inverse of what we did before. We're going to cross multiply. 20y equals 80. Y equals 4. Okay? That's the kind of stuff that we talked about last time. And you will still need to know how to do these. The only thing that's different with what we're going to talk about now is that we have situations where they're nested or overlapping in different ways. Or even these word problems. You need to be able to create diagrams for yourself there too. So we're going to talk about slightly different scenarios, but we're still using proportion and cross multiplication to solve. Great. So what I want you guys to do, the best strategy for nested diagrams, is to take this picture and draw the triangles separate from each other. Remember, that's the strategy we used in Unit 4 when we were trying to decide if triangles were congruent. We drew them separate. So in any situation with overlapping, it's a really good idea to do that. Alright, so what I'm going to do is over here I'm going to draw a miniature representation of this diagram right here. You can make it a little bit bigger, I just need to make it smaller on my screen so it can fit. Leave the room here blank so we can use that for the solving. We're just going to draw a little diagram for yourself with the 2 triangles separate from each other, and then we're going to label the sides as if they were separate. Alright, so let's start with the smaller triangle. What would the upright vertical side be labeled with? This is the one we're doing right now. What would I put here? X. The vertical side right here is X. What would the bottom side be? 48. And then the diagonal, 58. Okay. Now, it's the bigger one that you have to be more careful with. Okay, this side right here should be 40, right? But what should the bottom be? 60. You have to remember to take this and that and make sure you add them together. So the full length of the bottom is 60, and then how would I label that diagonal side? Y plus 58. That's the biggest mistake that people make that I've seen through all of my experience teaching this is people, when they see Y, they just want to write Y by itself. But this little section right here is not a side of a triangle. It's part of the side. So you have to make sure that you link those together when you're writing the labels so you can use the full expression correctly. Now that we've separated them, can you guys see how easy it is to see what corresponds? Just go boom, boom, boom just by seeing it visually. So that's why it's a really good strategy to do that. Right? What variable you guys want to solve for first? X or Y? Okay. So we're just going to start with the variable we're looking for. You're going to write down X. What does that correspond with in the other triangle? The 40. And then what's my second ratio that I would use? Two sides that don't have variables that are corresponding. I'm going to be using the 48 and the 60, but since I started in this triangle, make sure the 48 is on top. Okay. We're going to cross multiply, so I have 60x equals 20. So x is equal to 32. Right? Same thing for y. What would my proportion look like? Good. This one you have to switch that second ratio so it corresponds, or it comes from the same triangle that the y plus 58 came from. Right, then we're going to cross multiply. This equation is going to be a little bit longer. So 48y plus 2,784 is equal to 3,480. Take a second. What do you guys get for y? 14.5. So the general process of writing the proportion and cross multiplying is exactly the same as what we saw before. The only difference here is that I need you guys to make sure you separate the triangles so you can see what the full lengths are for each of them separately. Alright, this is the same scenario as this one. It's just been kind of translated into a real world scenario kind of question. So they're going to give you word problems like these where they may or may not give you a diagram. So if they don't give you a diagram, please make sure that you are drawing one for yourself. Don't try to do it with the numbers kind of swirling in your head. So for this one, they've given us a diagram. I know we have a tree and a dog, but you guys see how there are two triangles? Like this, we can create two triangles kind of using the vertical relationship of a tree is straight up and a dog when it's sitting is kind of straight up. So you can see that there are two triangles. So I'm going to do the same thing as I did over here. I just need to put the information into the picture. So it says the dog is 10 feet from the tree. So where would that go? This section right here. Okay. Then it says the dog's shadow is 4 feet. That would be that little section, right? Then it says the dog, while it's sitting, is 3 feet tall. So we're going to go from the bottom to the top of its head. And I'm trying to figure out how tall the tree is. Right? So represent that with an X so you have an actual variable there. This is the same scenario as over here. This is a nested diagram. We have a triangle inside of another triangle. So again, the best way to approach this is just draw a small, quick little diagram with them separate from each other and label the sides so you have everything kind of individualized between the triangles. So for the small triangle, I have 3 and 4. What do I have for the bigger one? The vertical side should be X. The horizontal side should be 14. That's you have to make sure you add them together. The full length of the bigger triangle is 14 on the bottom. Now that I have that, you should be able to see, boom, 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 boom. You can match out the sides really easily. X over 3 14 over 4. You can see how they correspond in the diagram. Cross multiply, 4x equals 42. X equals 1.5, I think. Yes? Alright. I'm going to let you guys attempt the next 3 on your own. See if you can figure them out. If this is not necessarily a nested diagram, but it would probably be useful to separate them so you can see how the sides work separate from being attached. This one is a diagram you're going to have to draw for yourself, and then this is a nested diagram, but one of the triangles has been reflected or rotated. So see if you guys can figure out this. Alright, what did you guys get for this one? Should have gotten 12. The interesting thing about this diagram is that this triangle on the left has all 3 sides provided. It has the bottom one, and then this one's 9, and this is 2 wide. But then this triangle only has 2 sides. So you have to be careful that you matched up the sides that are corresponding very carefully. Hopefully you guys got 12. That is correct. Now, this one is a word problem where it doesn't have a diagram. Okay, so you have to draw one for yourself. There are 2 ways that you can draw this diagram. It does not necessarily have to be a nested diagram. This one did have to be nested because they didn't tell you both of the overlapping shadows here. If they don't tell you both of the corresponding sides, then you have to make it a nested diagram. This one, they've given you the shadows for either of the 2 characters that are kind of in this question. So you could have drawn the picture 2 ways, so I'll show you both. Right. You can draw them nested like this already, where you have the little diagram like this, or you can draw them separate. I'm going to show you how to label either one of these so you guys can decide which one that you would prefer to use. So this one's talking about a flagpole. Obviously that's the taller of the 2 objects, right? So this is my flagpole. Right? That casts a 27-foot shadow. So if you guys were using a nested diagram, you would have to use a bracket to show that the entire shadow from the flagpole out is 27, full length. And then this one says that a person standing nearby casts an 8-foot shadow. So I have a little person, a little dude, okay? And then for this one, you'd put the 8, but only on that section where it stands for the shadow of the person. So if you were to draw it as a nested diagram, please make sure you include the bracket to represent the full length. But if they're separate, you can just write them on each line separately like that. We know the person is 6 foot tall, and I want to know how tall the flagpole is. So either one of these scenarios is fine. If you draw the nested diagram, you can draw them separate from there. Right, so if you want to go straight here, it's probably less work for you. But again, either one of those is fine. What would the proportion look like if I set it up? X over 6 equals 27 over 8. Yep. Either way you do it, that's what the proportion should look like. And your final answer should be 20.25. Yep. So everybody okay with that one? Now, this one's interesting because it is a nested diagram, but they are not oriented in the same direction. So for this one, when you redraw them, you have to be really careful. For this one, when we redraw it, see how it's kind of facing down? Downwards, the right angle's pointing down. This side is 16. This side is x plus 10. Did everybody get at least that part? Where the bigger triangle, you have to add the pieces together. This one inside, the smaller triangle, is 8 and 10. And the right angle is pointing this way. Now the reason why I drew those arrows is because the right angles are going to tell us what corresponds, right? With right triangles, they can be a little ambiguous if the side lengths, the legs are the same length. But here they gave us the hypotenuse for each triangle instead. So how would I write the proportion for this one? Using the little hypotenuse arrows, right triangle situation to help us match corresponding sides. How would I start the proportion? Okay, x plus 10, start with the variable. Now according to the way that these triangles have been oriented, this is not the hypotenuse. So what side would correspond over here? The 8. And then in this triangle, what is the hypotenuse? 16, and that would correspond to the hypotenuse over here, which is 10. So that's how you use the orientation of the right triangle specifically to figure out how they're corresponding. When you cross multiply, what do you get as your final answer? 2.8. Right? So they may not be oriented the same way. So use the cues within the triangles. Specifically, if they're right triangles, you can use the hypotenuse relationship to figure out what corresponds. If one triangle's inside of another one, it's a nested diagram. So you always redraw.
I mean, the proof is right, the hypotenuse.
The hypotenuse is always across from the right angle. Is that what you're asking, how to tell whether it's a hypotenuse?
I mean, like how did you know that it wasn't going to be like the regular way we usually do it? You had to use the right
Because the right angle is here in this triangle in the upper left corner,
Oh, and then-
but it's not in the upper left corner. It would switch positions. Alright, we're going to talk about similarity proofs. Again, these are very similar to the ones we did in Unit 4. All we're doing is taking the information that we know about the diagram, extrapolating it a little bit more to decide if these shapes are similar, or, do you guys remember CPCTC? We have things like that for similarity. They don't have abbreviations, unfortunately, because there are two different ones, and the abbreviations aren't as nice to say as CPCTC. But this one, it works the same way. If you know that shapes are similar, you can get other conclusions from that as well, like the angles are congruent or the sides are proportional, stuff like that. So we're just going to go through these briefly and see how we can use similarity in proofs. So for this one, obviously, what do you write in the first box? The given. So I'm going to write them in two separate boxes because it's a little bit wordy. ABC is isosceles with base AC, and angle 1 is congruent to angle 2. I'm just going to write them separately because not a whole lot of room. If you have room, you can write them in one line. Alright, now that I have the givens, I need to see what I can get from them. So once you finish writing the givens, let's go with them in order. What can I get from the fact that ABC is isosceles? Yes? Okay, why? Remember that when you guys have an isosceles triangle, we do know that two sides are congruent, but what else do we know? Two angles are congruent, right? And the reason why they told you what the base was, this one, is so you can tell where the base angles are. Okay? So just like Tatum was saying, this angle right here, BAC, is congruent to this angle, BCA, because of the base angles theorem. Okay. I also know that angle 1 and angle 2 are congruent. Right? Notice that my proof statement wants us to prove that AE over CD is equal to CE over BD. How would we get a proportion like that? Where would that come from? What would we have to have first as a foundation in order to get a proportion of corresponding sides? Well, we don't have any side lengths, so we have to work off of other things. What would I need to know first in order to say that those sides are proportional? Congruent with Unit 4.
Oh, I meant,
Similar. We need to prove the triangles are similar. If we know that the triangles are similar, we can then conclude that the sides are proportional because that's the definition of similarity. So do I have enough information currently to prove that we have similar triangles? Yeah. What rule? Angle. Now what you guys have to do is tell me which triangles and name them correctly. Go for it. EAC is one of them. Similar to? What corresponds to E? So D and E both have that double mark, right? A has a single mark, which would be C, and then B, right? Those two triangles are similar by analytical similarity. Right. Now that I know the triangles are similar, based on that definition, can I say that the sides are proportional? Yeah. So I can go straight to my proof statement. AE over CD, which are corresponding, is equal to CE over BD. right? Now the reason that we're going to write for this is very similar to CPCTC, right? Remember that stands for corresponding parts of congruent triangles are congruent. That's what CPCTC stands for. We're going to write the same thing here, but the wording is slightly different, and I don't want you guys to have to bother memorizing another tongue twister thing, so I'm just going to have you guys abbreviate, right? How can I take that CPCTC idea and reword it so it applies here? Corresponding, what am I working with? Sides. Corresponding sides of similar triangles are proportional. So it's the same idea, you're just switching what we're working with, you're switching to similar, and now you're taking congruent, turning into proportional, right? So it's the same idea, it's just CSSTP, not as easy to memorize, right? So for this one, just write it out so we can see what's going on here. That's it, that's it. Okay, is everybody okay with that one? Okay. This next one is a straightforward, just prove the triangles are similar. Okay. All that we know right now is that these two triangles are equilateral. So let's go ahead and write that down. STU and VWX are equilateral. Okay, so I know this, right? They're equilateral but separate from each other. So these three sides are equal and these three sides are equal, but we don't know a relationship between them. Okay. So, what would I do from here? Let's just brainstorm before we keep going. What would you think would be the next step here?
Say that the angles are congruent.
Okay, so we can go from the fact that the sides are equal to saying that the angles are equal, right? And if I have that, would that be a foundation I could use to prove that the triangles are similar? Yeah. So let's take that and let's work through that to actually write it within the proof to get to that final conclusion. So all I know right now is that the triangles are equilateral. You guys want to switch the idea of the angles being equal. Do you guys remember what that's called? When you say that the angles are equiangular. Yep. So we can go from the fact that they're equilateral, and then we can switch to them being equiangular. Are equiangular. Now this is not a specific theorem, this is not a specific definition, it's more like an axiom, something that we just know to be true. So the reason you would put here is equilateral triangles are equiangular. It's kind of just a property of those triangles that they're interchangeable, both exist at the same time. Right? So we can switch our thinking from the sides to now the angles. So remember, what rule are we aiming towards using for similarity? We're aiming towards angle. So within your proof, you need to specifically show me one set of angles are congruent, a second set of angles are congruent, and then you can get that result for me for the triangles being similar. So you guys just need to pick what angles you would like to do and then write them out in a congruency statement.
Did you have to write that statement right there about equiangular, or can you just list all those sides? Angles.
You would have to go here first because you need the fact it's an equiangular triangle first before you can say the angles are equal. Alright, so just pick two. What's the set of angles that we know are congruent? We know T and W are congruent, so we're going to start with that. Alright, we can say, definition of equiangular. Right? What's another one? Because I need two. What? S and V. You could have chosen U and X, whatever, doesn't matter as long as you have two. This is definition of so now I have this, and I have this. So are the triangles similar? Yes. We go straight to that proof statement. By angle, similarity. Okay, everybody clear on that one? Alright. That was like a small picture proof that we learned in Unit 4. The first one's a big picture. We had to take, or sorry, no. That was a big picture proof where you just prove in general that they're similar. This one and the first one are small picture proofs, like I referred to in Unit 4, where I first have to prove that the full picture is similar, and then I'm going to zoom in on specific parts. Right? So that's what's happening here too. I need to prove that CA and DE are parallel based on the fact that I have these other things here. Okay? So the first things that I know are that BA and CD are parallel, and I know angle A is congruent to angle E. Okay, this is what I know. What can I get from that? Okay, can you name them? No, because it's too ambiguous with C here. Angle C can be here, here, or here. So when it's ambiguous, you have to use 3. So for this one, we have angle ABC is congruent to what? DCE. Make sure you use 3 letters when it's an ambiguous angle, which means that there are more than just 2 segments going off from one vertex. And why do I know that those are congruent? Corresponding angles postulate. Okay, now remember, I'm ultimately trying to prove that these 2 lines are parallel. How can I get there? What would I need to know in order to get that those lines are parallel? I need these 2 to be equal, right? The other set of corresponding angles to be congruent in order to get those lines parallel. Well, how can I get that those angles are congruent? Through the avenue of similarity. Have we said that the triangles are similar? Okay, so we can first use angle to show that these 2 triangles are similar, right? So I can have triangle ABC is similar to triangle DCE by angle, using the angle that was given and the ones that you just found, right? Now that the triangles are similar, do you guys remember the definition of similarity, right, with similar triangles, not only says that the sides are proportional, what does it say about the angles? Well, the angles are equal, okay? So now that I know that the triangles are similar, what do I know about these 2 angles? They're congruent. So now I can say ACB is congruent to DEC. And how do I know that? Kind of briefly explaining like we did up there. Corresponding angles of similar triangles are congruent. Again, like CPCTC, but you have to word it differently for similarity. Corresponding angles of similar triangles are congruent. Now, is that enough to say that the lines are parallel? Yes. Using what? I can now say that these 2 lines right here are parallel using what? It's the corresponding angles postulate. Converse. Since we're going from angles to parallel, we're going in the opposite direction this time. It's still a corresponding angles postulate, but it's the converse. Right? So these proofs, they may ask you to find arbitrary things that are parallel or proportional or equal. You guys have to take the avenue of similarity first and then use the proportional sides or the congruent angles of similar triangles to get to that final result. Okay? That's really the focus of the proofs in this unit. Everybody good? Okay, that's it.